Hi to everybody who is watching this video presentation, and thanks to the organizer of the WIN 2021 workshop for giving me the opportunity to talk about my work on neutrino decay and its relation to the cosmological neutrino masses. This is based on the work we published last year together with my two PhD supervisors here in Valencia, Jacobo López Pavón and Nuria Rios, and with Miguel Escudero, who is a former PhD student of Nuria and now postdoc in Munich. So let me get started directly with a takeaway message of this talk, which in the following I try to outline and explain a little bit. The motivation of this talk was very clear, as a current cosmological measurement by Planck and Bau are more than 1 order of magnitude stronger than the best laboratory bound we have so far set by Catherine. And this, together with our knowledge of the active neutrino mass splitting from other experiments, from cosmologically inferred neutrino mass bound seems to rule out already the possibility of having degenerate neutrinos, as well as on the limit on testing the inverted or normal hierarchy scenario of the neutrino masses. From a model perspective, this bound may also be sort of challenging, as many flavor models which successfully can explain neutrino oscillation data results in a 2-0 texture of the neutrino masses, which generally predicts the neutrino masses to be higher than 0.12 electron volt. However, one has to realize that this cosmological neutrino mass bound is dependent on the underlying cosmological model, which in this particular case is the lambda CDM standard model equipped with stable neutrinos. Relaxing this assumption on the stability of the neutrino, however, you can find that the bond can be loosened to up to 1 electron volt, and we show how this can be incorporated in somewhat famous U1 mu minus tau model. Okay. So to understand how such a relaxation is possible, one needs to realize that the constraining power of Planck on the neutrino masses arises from its contribution to the non-cold dark matter component today. Okay, and this is why changing the lambda CDM model with, for example, an early dark energy phase or whatever typical lambda CDM extension you have in mind does not change really the bound of 0.12 electron volt. At most a factor of 2, but will certainly be much stronger than the best laboratory bound we have. And this we illustrate here to illustrate how different neutrino masses contribute to the total energy budget of the universe. We show here the evolution of different energy densities as the photons, neutrinos, dark matter baryons, and the cosmological constant over the course of the cosmological history, characterized by an energy density, normalized energy density omega, and the scale factor A, which can be read as a time variable. Okay, and the gray vertical lines indicate some important cosmological events and when measurements are active. And we see that the 3 purple lines, which is the evolution of the energy density of the neutrinos, evolve very differently at late times, but the same at early times until recombination, which is basically the time of the CMB formation. The only difference of these 3 lines is the mass of the neutrino fluid, ranging from 1 electron volt to 0.06 electron volt, which is only realizable in the normal ordering scenario. But in these 3 cases, the neutrino fluid is taken to be stable. Okay, so let's see what happens if we actually allow for neutrino decay. And then the plot looks like this, where we had the 3 purple dashed lines. Okay, showing the neutrino energy density evolution for the same masses, but now with some decay rate, which is faster than the age of the universe. Okay, so obviously in this case, the neutrino decay away at late times, and its contribution to the non-cold dark matter energy density today gets drastically diluted away, and the main constraining power of Planck is circumvented. But note, however, that at early times, the evolution is basically the same as in the stable case. So the only difference is at late times, but this is the main constraining power from Planck. And so this opens the possibility that neutrino decay can relax this 0.12 electron volt bound to some higher extent. So now the question should be how such decays can be achieved, or more precisely, how to achieve such a decay with the desired decay rate, which certainly should be faster than the age of the universe. And as a starting point, you can look in the Stefan model, because once neutrinos are massive, they certainly will decay away. But it is no surprise that detailed calculation of radiative neutrino decays show that this will only happen on timescales which are much higher than the age of the universe. Okay, which is basically as the proton, which does not decay within the time of the universe. So this is why certainly some extent of beyond the standard model physics are needed. So what we did in our work is to collect all possible neutrino decay channels, which can be characterized by two model-independent renormalizable Lagrangians, and classify them into two categories, which are first, how many active neutrinos are in the final states, and second, how many final states particles you have in total. Okay, so after analyzing all possibilities, the most promising one is a two-body decay, because three-body decays are either ruled out entirely, or the variable parameter space requires such a strange coupling or scale hierarchy that we find it very unlikely to realize it in concrete models. In any case, the variable parameter space of three-body decays is tiny, and we concentrate here on two-body decays. So we are left with the two decay types when active neutrino decays into another active neutrinos plus a BSM light scalar or vector boson, or the second possibility where you change the active to a stereo neutrino. Okay, so let us analyze first just the decay of the type when one active decays into another active, as it is the most minimal scenario. And in this case, as we know, the lightest neutrino has to be stable. So the relaxation of the neutrino mass bound from cosmology is entirely controlled by the measured mass splitting of the three active states. And this here we show this by comparing the from cosmological measurements inferred neutrino mass, which if all neutrinos have decayed away is given by 3 times the lightest neutrino, versus the actual physical mass. And here in this plot, the horizontal lines indicate the Planck bound on 0.12 electron volt, which is set on the cosmological mass, and the future expected sensitivity of Deci and Euclid. So to compare the physical and cosmological mass in the stable neutrino case, it is obvious that the relation between these two masses is 1-to-1. Okay, and this is represented by this black dashed line, straight line in the middle of the plot. Whereas in the decaying neutrino case, the relation depends on the ordering, and the green line here is the normal ordering scenario, and the red line the inverted ordering scenario. And obviously, as we go to smaller and smaller light neutrino masses, which actually can be vanishing, the effect of such an active mass eigenstate transition, to say one active neutrino decays into an active neutrino plus a scalar vector boson, becomes more and more important as the relative size of the mass splitting to the lightest neutrino grows rapidly. The relaxation of the Planck bound is somewhat tiny, as you see here from 0.12 electron volt. We cannot do much, but it's very important the interpretation of the future or possible future signal of Deci and Euclid. Let's take, for example, a hypothetical measurement of Deci and Euclid, which is on the lower limit of the 1 sigma range of 0.04 electron volt. Okay, if Deci and Euclid report a value of 0.04 electron volt of the sum of the neutrino masses, this would exclude inverted and normal hierarchy neutrino mass model, which is in conflict with everything we know about neutrino physics and also every other experiment. However, if we incorporate neutrino decay into this case, this can reconcile the Deci or the possible Deci Euclid measurements with a normal and inverted hierarchy scenario. So this makes neutrino decay, given the future sensitivity of such cosmological measurements, very, very important. And here for the case of a stereo neutrino in the final state, so to say that one active neutrino decays into a stereo neutrino plus a scalar vector boson, the mass bound can be relaxed much, and the parameter space of the relaxation of the mass bound is much bigger. And the main constraints here arise from CMB free streaming, or the perturbation of the neutrino CMB free streaming in the relativistic regime, as well as in the non-relativistic regime on analyzing the CMB and large-scale structure. Okay, in this plot here, everything which is white and on the right of this yellow dashed line, which is the Planck bound on cosmological stable neutrino masses, everything which is white is allowed with a certain decay rate given on the y-axis. So let us now turn to a more practical question of how such a model can be, how such a decay can be realized within concrete models. So to this end, we analyze the famous U1 mu minus tau model, which imposes a symmetry on the accidental symmetry of the standard model, which is anomaly free with free right-handed neutrinos. Okay, and in this context, the extra degrees of freedom we have to add to the standard models are exactly these three right-handed neutrinos, which can be the typical or standard seesaw Majorana neutrinos explaining the measured light neutrino masses, plus a charged complex scalar. The resulting light neutrino mass matrix is a 2-0 texture, or in this case is the inverse of the light neutrino mass matrix, which has a 2-0 texture. And upon diagonalizing it with the UPMNS matrix, with given the latest values of the new fit collaboration on the mixing angles of the light active states, one can find that at 3 sigma, the predicted masses are 12.6 milli-electron volts, okay, which is in conflict with a reported bound of 0.12 of the Planck collaboration. However, this model immediately allows for neutrino decay of the type where one active neutrino transits to another active neutrino. So this can already be used to somewhat relax the tension between the Planck reported value and this predicted value of the neutrino masses. But however, if we have one stereo neutrino in the final case, we can do better. So let's see what we can do. And to this extension, the simplest extension is given by a U1X symmetry under which a complex scalar and the fermion singlet are charged, such that the unique new type of the Lagrangian are given by this interaction term, and the resulting complete neutrino mass matrix is of 7 times 7 and of this type. Okay, and now assuming a scale hierarchy of the classical type, that the Dirac mass is smaller than the Majorana scale, but also that the new mass scale is smaller than the Dirac mass scale, the typical seesaw mechanism is at work, and it also ensures the right stereo neutrino properties which we need. That is that the tree level, the stereo neutrino mass is vanishing, and also that the loop corrections are tiny. That is, the stereo neutrino will always be lighter than one of the mass eigenstates of the active neutrinos, and also the mixing of the stereo neutrino to the active neutrinos are small. Okay, so all the oscillation data are in accordance with the model. Analyzing this model, and we can see that the resulting neutrino decay rate can be parameterized by this formula, where we take as a reference value of the summed light neutrino mass is 0.3 electron volt, and the reference scale for the Majorana mass to be 10 to the 14 GeV. So, and then the resulting plot looks like this, where the constraints are as before from CMB and large-scale structure analysis, and the red bands here indicate the 1 sigma and 3 sigma mass prediction, giving the latest new fit data on the mixing, on the light active neutrino mixing angles. So we see that there's a lot of space within the model where the Planck mass bound can be relaxed by up to one electron volt, and the relaxation is within the model mass prediction, which can be realized with a somewhat nice Majorana scales and Yukawa couplings. On the last slide here, I leave you with a summary. And if you go to this archive link of this work, you can find much more details for everything what I tried to explain to you now. And we hope to have data of this neutrino in the next 5 to 10 years to test such a neutrino decay scenario. So thank you very much for your attention watching this video. And I hope to see you on Slack and Zoom discussion next week. So thank you very much. Bye-bye.